last section of material in this chapter, 3.7, is called related rates. Now we're about to use something that you've seen before from chapter 2 that you didn't particularly like. We're going to use it in a very cool way to show why in the world we ever would have done it to begin with. Because when you learned it, I know you were thinking, why in the world am I doing this? And it has a very applicable reason that you're about to get to learn. Okay? It's easier here than it was there. That's something else to be aware of. Kind of like these derivatives, right? We made horrible, ugly derivatives for you to find, right? Like skills quizzes and things like that. And then now that we're actually working problems for optimization and stuff like that, for the most part, the functions are easier to work with, right? Same kind of thing is going to happen here. All right, so related rates. Related rates are the idea of something changing in relation to time. Okay, so quantities are changing in relation to time. So, for example, I had a student do an example of a related rates question in my methods class the other day. He's going to be a math teacher in the high schools, right? He was talking about related rates. Obviously, he thinks he's going to teach some kind of calculus, or maybe is interested in doing so. And he talked about a baseball diamond. Okay, so imagine a baseball diamond. If somebody's running from first to second, then their distance that they're actually getting closer to home plate would be decreasing, right? And it's all related to the amount of time that passes. So that's what we're going to be looking at in general as we look at these questions. So kind of like in the last section, I'm going to give you some steps by which we do this to think through. Sketches are very appropriate. They're extremely helpful. Okay, so when it's appropriate, draw a sketch. Equations. We're in a math class. That should be no surprise. You're going to have an equation that relates the quantities together. Step 3 is the step that I was referring to. You're going to differentiate. How? Implicitly. Implicit differentiation. But I promise it's easier to do here than it was before. Okay, so just take me at my word for the moment and I'll show you. Implicitly differentiate both sides with respect to time. That's what's going to make this different. Step 4, we're going to substitute in known values, and step 5 is we're going to solve for the remaining rate. So it's really like the calculus step is the one in the very dead center of this one. Last time with optimization, the calculus step was the very last one that we did. Here, the calculus step is dead center of what we're doing. We're doing a little bit of algebra and setup beforehand. We're doing a little bit of algebra stuff afterwards. Calculus in the middle. All right. I think an example would make a lot of sense, don't you? Because you still don't know what I'm talking about, right? No idea. Okay, here's an example. A fish. A fish is reeled in at a rate of 1 foot per second from a point 10 feet above the water. At what rate is the angle of elevation theta between the line and the water changing when there is a total of 25 feet of line from the end of the rod to the water? And I got glazed looks on everybody's faces. Even if you like fishing, you checked out, didn't you? This problem's not really all that difficult, but it looks massively confusing, doesn't it? It really does. It's very wordy. But what we're going to do is we're going to try and simplify it by drawing a picture that relates all these items together. Okay, so my picture is that somebody's fishing. And they're fishing above the water, and more above the water than their height, because they're obviously not 10 feet tall. So far, so good? So they're on a pier, they're on a boat, I don't know, but they're at least a distance above the water that's about 10 feet. So the first thing I'm going to do is I'm going to draw in my water. And we're going to put our guy up here 10 feet above the water. So far, so good? Oh, I should draw my guy. Here's my guy. That's as good as you're going to get from me on a person. Stick figures. And he's fishing, and when you fish, you know, the fishing line's not right here in front of you, right? The fishing line's out there somewhere further away from where you are. So he's got his little fishing pole, and he's out here somewhere is where his fishing line is. And we have a fish over here. Already, you should see a geometric figure in this picture that already helps to make the problem make more sense. What's the shape? It's a triangle. We're dealing with stuff about triangles, which should make you think a lot about trig, right? Trig, triangles, unit circles, stuff like that, that's trig. So this one's trig. Now let's go back to the other information that we're given. It says the fish is reeled in at a rate of 1 foot per second. So this line that's out is being reeled in. So right now, it tells you that there's 25 feet of line, okay? But, you know, it says 1 minute or 1 second from now, it will be 24 foot of line, right? And then another second, it's going to be 23 foot of line, because that's how fast he's pulling this fish in. Is everybody good with the description so far? So this length right here, let's give this length a name. What do you want to call this length, this our fishing line? L would be good. I want to avoid X and Y, and here's why. Usually we mean X as a horizontal distance, and we mean Y as a vertical distance. And I don't want us to confuse those quantities, so let's give it another name. L would be okay. If you wanted to use H for hypotenuse, that would make sense. You could use Z just as X, Y, Z. It doesn't make any difference what it is, but try to avoid things like the letter S. S is not a good letter to use in math because it probably looks a lot like some of your 5s. You with me? T is equally as bad because it looks a lot like plus signs. So avoid S's and T's and we should be pretty good otherwise. Sometimes Z's will look like 2's if you're not careful as well, so you need to be careful on that one. All right, so we'll use L since Snyder suggested L. And what we're being told is that this L has a rate, and the rate for this L is that it's decreasing. What does rate mean in calculus? When you hear the word rate, it should mean something. What's that? It is in relation to time here. Oh, so you're seeing something like, let me write down exactly what you just said. Change. In this case, it's change in distance over change. I can't get it written. In time. And then I heard somebody say something else after that. Slope, velocity. I'm waiting for one more word. Slope, velocity. Oh, who said it? What'd you say, Akil? Derivative. This is a derivative. A rate is a derivative. That's all it is. So what is it the derivative of? Well, this is, and we're going to use notation that we didn't use much before. This is dl, the change in the line, dl, over dt, because just like Jacob said, it's the change in time. This dl dt is related to that particular side of my triangle, dl dt. And we know that dl dt is actually 1 foot per second. Now, let's pause for just a second. Is it positive 1 or is it negative 1? It's actually negative. Why? It's being reeled in. Yeah, that distance is decreasing, so it is a negative 1 foot per second. All right. 10 feet above the water, at what rate is the angle of elevation theta? Where's theta? Good, between the water and the line. Okay, so let's put the theta in now. Here's theta. And we're wanting to know what rate the angle of elevation between the line and water is changing. So what is it that we're actually asked to find related to this? Rate is d theta dt. It's the change in theta with respect to the change in time. It's a derivative. And this is the quantity that we don't know. Good so far? We do not know that value. We do not know that value. There is no, we could also talk about in this problem, if it related to what the question's being asked, there would be a dx dt. Obviously, this length is changing, right? It is definitely changing as this fish gets reeled in. The 10 feet does not change, though, right? It's a constant. So even though I put the y here, I don't want to use y in this equation that I'm about to set up at all, because this is a value that does not change. It is always 10. You with me? So we have to be really careful with related rates, because in related rates, some quantities are constant. They do not change. Others do. For instance, L equals 25 is only at this particular point in time. 1 second from now, it's not 25, right? It's changing. So we want to make sure that when we're doing our equation here in a moment that we use L and not 25 as we're doing the equation, because the L value changes with respect to time. All right, we have a triangle here, which means that depending on what we're asked, what are some relationships inside of triangles that you know? Pythagorean theorem. That's what we would use if we were asked to find something about the x or the dx at the bottom, right? We would relate the x, we would relate the 25 feet of line, and the 10-foot, we would relate the sides of the triangle. What else do you know about triangles? What's that? They're 180 degrees. That's true. It's not going to help us in this particular problem, but that is a true statement. What else? All right, so trig functions, right? Sines and cosines and tangents. Those are values that matter in terms of triangles. So we have to figure out, in terms of this triangle, what trig function is useful. Which one? Sine. So Mackenzie thinks sine. Do you see why? You see, the sine value would relate the opposite side, which we know, to the hypotenuse, which we at least know something about at different points in time. We don't know anything about x, so I don't want to use x, and both tangent and cosine would use x. Make sense? Fantastic. So the correct relationship that we're looking at for this particular function is the sine relationship. Sine of theta equals. Now let's take a look at what it actually equals in terms of this problem. It's a ratio of the opposite side. What is the opposite side? 10 over the hypotenuse. And what is the hypotenuse? It is L. Be careful. It is L because it changes over time in general. So we have the sine of theta equals 10 over L. All right, let's go back to my steps here and see where we are in the process. Number 1, we created the simple sketch. Number 2, it says set up an equation relating all the relevant quantities. We did it. We're done with steps 1 and 2, which means we've yet to do any calculus is what it really means, right? I mean, I wrote some calculus down, the dx's and the dy's and the dt's and the dl's and the whatever d's. I wrote all that stuff's calculus that I wrote down, but I haven't done anything with it, okay? So I've sort of mixed step 2 and step 3 together. Step 3 says that we're going to differentiate implicitly both sides with respect to time. This is where the process is going to change a little bit from what we did before. Okay, I'm going to take this equation. We're going to go to a new screen so that we have a little more space to work. All right, sine of theta equals 10 over L. We can leave it that way. It's okay. But I think it probably would be easier to rewrite this as sine of theta equals 10 L to the negative 1. Then I don't have to use a quotient rule. If you really like the quotient rule, just use it. That's fine. But I just as soon use the power rule if I can. So, all right, we need to differentiate implicitly with respect to time. What is the derivative of sine? Cosine. Good. Cosine of theta. But then we have to take the derivative of theta. It's the angle inside with respect to time. This is where this looks different. The derivative of theta with respect to time is d theta dt, which is in fact the quantity that we're looking for, which we said a minute ago. Every variable now is taken as in the same way that we did y when we did dy dx's last time with implicit differentiation. Every time we have a variable, we're going to have d of that variable dt. Every single time. So let's do the right-hand side so you can see it happen again. What is the derivative of 10L to the negative 1? What am I going to do with the exponent? Negative 10L to the negative 2. And then L is a variable, which means that the derivative of L with respect to time is dl dt. Every variable will have d, whatever the variable is, dt, when you take the derivative of it. What you've really got going on is you have multiple chain rules going on, because the inside of every function is a variable with respect to time. Okay, Now we actually know some of these values. This is a kind of a mess the way it's written, so I'm going to clean up a couple of things. We know that this is cosine of theta, d theta dt, nothing to simplify over there. On the right-hand side, however, I could write negative 10, over L squared, and then dl dt. Now, some of these things I know. So taking a look at this, back on my other screen, tell me a quantity that you know that we can plug in, just one. dl dt. What's dl dt, Allison? It's -1. Fantastic. So this is the substituting step. Here's a -1. We know that value. Which value is it that we for sure do not know because we're looking for it? d theta dt. So I'm going to go ahead and write d theta dt in, recognizing that I don't know that value right now. Which must mean that theta and L have values, or have values I can find based on the information I was given. One of them is given to us. Which one? L is 25 at this specific point in time. So now's the time when I use that information. L is 25, so this is 25 squared on bottom. Now, correct me if I'm wrong, but they really did not tell us theta equals something, right? They didn't. But can we find it? Yes, we can. Josh, you seem to have an idea of how you might do that. What were you thinking? Okay, so there's some kind of relationship, trig relationship, that helps us find theta. Don't think it's tangent, though. Yeah, I thought you did. Maybe I heard you wrong. Sine? Okay. 10, that's the word I heard you say. Okay, no problem. Okay, sorry, I'm at a distance away, so I'm at a disadvantage. So yes, sine is correct. So sine of theta equals 10 over 25 is the relationship. We know it's sine of theta equals 10 over L, and L at this specific point in time is 25. So I can use this information, and how am I going to actually solve for theta instead of sine of theta? Do you remember? Inverse. Good. Your calculator, if it's set up in radians, which it should be, should then give you the correct value if you use the inverse sine of 10 over 25. We do want a radian value. We do not want it in degrees. Here we're solving, what was that? T equal to 1. It's not T equal to anything. This isn't the derivative formula. This was the original formula. The original relationship that we set up over here before we took derivatives. Why did we plug 25 in? Because this is the exact moment in time when we're wanting that information. And at this exact moment in time, the line has 25 feet. The time is 0 right now. Yeah, this is sort of the 0 moment of time, exactly. Because at one moment, if we talked about 1 second from now, like what you're suggesting with t equal to 1, we'd actually have 24, right? Because it's reeling in at a rate of 1 foot per second. What value did we get for theta? Let's go ahead and keep theta with 4 decimals for the moment. Say again for me. 4115. Awesome. Which means over here in my problem, we can do cosine of 0.4115. All right, so a few things with this. On the right-hand side, this is end up being positive because I've got -10 and -1. So I really just have 10 over 25 squared, and 25 squared is 625, I think. I'm eventually going to have to divide by the cosine value that I just looked at, right? The cosine of 0.4115. All right, so a little bit of algebra here at the end to substitute these in. And then to simplify this to say d theta dt on the left. And what value do we get for d theta dt? And your book is consistently using 4 decimals, I believe, on this one, so we will use 4 decimals as well. What do we get for d theta dt? We type 10 divided by 25 squared, hit enter, divide 0.0175. Okay, does that numerical value look okay to everyone? Is your calculator giving you that as well? If it's not, please let me know, because we might need to take a look at the calculator issue. Okay? But this is an application problem, which means that this value has units to it. And the cool thing is that if you've written it properly, in this notation over here, it tells you how you determine the units. The units are the units on theta divided the units on time. What are the units on theta in this problem? Radians, exactly. So this is radians per the units of time. What unit of time? Seconds. This is radians per second. So this is a little weird, isn't it? It's a little bit weird. Let's at least get the next one set up. We don't have time to probably do the whole thing, but let's take a look at the picture and see how far we can get into creating this particular image. Here we have a balloon, spherical balloon specifically. A spherical balloon is inflated with gas at a rate of 800 cubic centimeters per minute. How fast is the radius of the balloon increasing when the radius is 30 centimeters? The last thing I want you to do when you get into these problems is get overwhelmed by the language. Do what you can, and if all you can do is draw the picture, that's worth something, okay? So do what you can. This tells you to draw what? A balloon, a sphere, right? A circle. So we're going to draw a circle and we're going to make it look like a sphere, and if you weren't sure how to do that, you're going to learn today. Okay, so you're going to draw a circle, and the way that you make it look spherical is by doing a line like this and a dotted line at the back like this, and all of a sudden it looks a little bit like a sphere. Okay? I don't draw well, but I can do this one, so I think you probably can too. I'm going to put a point here in the middle just to recognize that there is a center point to my sphere, and the reason that that matters is because it references a few things. What are some of the things that it references that I might want to draw on the image or to write down as a quantity that's of importance to me? The radius. So you can draw the radius wherever you'd like, but it takes from the center point wherever you are out to the edge of the sphere. So there's the radius. At some point, this radius is a given 30, but not always is it 30, right? We're adding air to the balloon, or in some situation we might be taking air away. But the radius is changing. What other quantity is it in this balloon that's important to us in this problem? The rate of increase of what? Cubic centimeters. What do you think we're actually changing in this problem then? The volume, right? This is all about volume. So this is probably not a formula that you remember, but does anyone remember the volume for a sphere?
Is it 4/3 pi r cubed?
Wow, well done. I don't think that I could come up with that if I were in your shoes. 4/3 pi r cubed. That's exactly right. I have no intention of making you guys remember obscure formulas. So if I have something on there that's like a sphere or something, I will make sure and give you the kind of a formula you would need, okay? So this one is 4/3 pi r cubed. All right, well, there's one more piece of information that I can write down. It has to do with that 800 cubic centimeters per minute. What is that a rate for? Change in volume, dV dt. Good job. dV dt. Couple of things telling you that. Number one, it doesn't tell you how the radius changes. In fact, it tells you that that's what you're looking for, right? So there's only two letters in this problem, V and R. So it has to be one of them. The 800 has to be going with the V or the R, and it's a rate. So this is 800. The reason for sure also that you might recognize that it's dV dt instead of dr dt is it's cubic centimeters. What does cubic centimeters actually mean if I write it down in notation? Centimeters cubed, right? Cubic is a volume measure, not a linear measure. So this is centimeters cubed per what? What did it say? Minute. Awesome. And what we're asked to find in this problem is we're asked to find dr dt. That's the question. What is dr dt? Specifically when r equals what? 30 centimeters. We're going to do one last thing before we quit today. We're going to take a derivative, okay? What is going to be the derivative of v? What's the left-hand side going to become? dv over dt. Well done. How about that right-hand side? 4/3 pi r cubed. Awesome. Okay, so the 3 comes down to cancel out the 4/3 to be a 4. We decrease the power on r by 1, and then every variable becomes that variable, d of that variable, over dt. We will pick up with this problem next time.